So let's start by talking about what a complex number is. So normally we deal with things in an XY coordinate system, right? So if I have a point up here, that point has some coordinates x of 1 and y of 1, right? And we can draw a line to that point, and we know that this distance here is x1, and this distance here is y1. So not dissimilarly, we can do something very similar using another square style axis, but we'll call this x-axis. Instead of x, it'll be our real axis, and this y will be our imaginary axis. So similarly, if we have that same point, that now has a real component and an imaginary component. Okay, so if we draw a line to that, we now have our magnitude of the real component and our magnitude of the imaginary component, right? So it works out pretty much the same. The only thing that's a little different here is this plane we usually deal with in polar because it's a little bit more straightforward, and complex numbers are rotational, which is a little bit out of the scope of what we're going to talk about today. It's just a good piece of background. So with that in mind, there's a couple things that we have to consider, we have to remember. So we know some relationships in polar that will give us side lengths if we have a hypotenuse. So we know that x is going to be r cosine of theta, and y is going to be r sine of theta, right? That's stuff we should know by now, hopefully. And if not, it's pretty straightforward to prove using your unit circle and your Pythagorean identities. And your SOHCAHTOA, mostly. Okay, so keeping that in mind, that shows you can kind of see here, well, this x goes to this real, which is your adjacent side, and it's related to this hypotenuse. Okay, that makes sense, that's cosine, right? And we have cosine, so it works out. And the same thing for imaginary, except with sine. Okay, so let's dive into a couple of these numbers real quick. So let's start with, if we have the number 1 plus I, this one should be pretty straightforward. So this is saying I have a magnitude of 1 in my real, and I have a magnitude of 1 in my complex, in my imaginary. So that, we could say that that's right here, that's fine. That number is useful, it's in rectangular, but I think it's easier if we change it to polar. So let's do that. So changing to polar can trip people up, but it's not terrible once you do it a couple times. So what we're going to want to do here to change this to polar is we're going to take, just like we normally would if we wanted a radius and we have a real and an imaginary, we'll take our square root of the sum of the squares. So if I take the square root of the real part squared plus the imaginary part squared, that'll equal my r. Okay? And then to get my my angle, because I'm going to polar, well, I know this angle here, this theta, it's also given, if I have the opposite and the adjacent components, it's given by a tangent function, right? An inverse tangent. So tangent is opposite over adjacent, so that's imaginary over real. So that's tangent theta. So now I want inverse tangent, and that's going to be imaginary over real. And that equals theta. Okay, but armed with that information, we should be able to solve this problem now. So this is 1, so this will be pretty straightforward. So we're going to go to our square root. The real part is 1. Now, people also struggle with this part a little bit as well. When you're taking the imaginary part, you need everything attached to the I, but you don't need the I. So in this case, we're just taking another 1, right? And both of these are squared, and that's all within our square root. This will equal r. So then that's 1 squared is 1, plus 1 squared is 1, so that's 2. So we should have square root of 2. Nothing super special there. Okay, so now we have the inverse tangent, and our imaginary part again is just going to be 1, and our real part again is just 1. So the inverse tangent of 1, well, that's where sine divided by cosine is 1, and sine divided by cosine is 1 when they're equal. Well, they're only equal at one type of point in our negative pi to pi. They're going to be equal and positive 1 when you have an angle of 45 degrees or pi fourths. And both those angles are valid. I like radians because this is a calculus concept, so I may use pi fourths. In your engineering classes, you may use 45 degrees. Just depends on what you're working on. Okay, all we have to do now is represent these two things in one number. So our standard form for polar is going to be r angle theta, or you may do r cosine of theta plus I sine of theta. Those are both exactly the same. So either is totally valid. A lot of times in electrical engineering we use this notation here, which is, we call it phasor notation, but it's also still just polar. Most of the time in your math classes you'll use this cosine sine representation. They're both the same. So let's go and plug everything in real quick. We get root 2, and then we have our angle and pi fourths. Easy peasy, that's our polar. And now if we want to go backwards, that's also pretty straightforward, because in this case we'll use this one just because it's a little bit more visually convenient. So if we have root 2 times cosine of pi over 4 plus I sine pi over 4. Well, cosine of pi over 4 we know is root 2 over 2. So this root 2 is going to stay here. And then I have root 2 over 2. Right? And then here, I stays out, nothing changes there, and then sine of pi fourths is root 2 over 2. Okay, well let's multiply this root 2 through the entire problem. So root 2 times root 2 is going to be just 2. 2 divided by 2 is 1, so I get 1. And then the same math applies here, so I get I. So negative root 3 plus I. Okay? So we're going to do the same thing. We're going to turn this into a polar number, and then we may skip the part where we go back, just because I don't think that there's a ton of value doing that a bunch of times. I just wanted to show that we were doing everything the right way. So let's start by dealing with the radius component. So we have our r, which is equal to the square root, and now I have negative root 3 squared plus, remember we don't need the I, we just need what's attached to it, so it's going to be a 1. So 1 squared. Okay, well, negative root 3 squared is just going to be 3, and then plus 1, so that's square root of 4, which we know is just 2. So our radius in this case is 2. Okay, our theta is going to be tangent negative 1. Our imaginary is 1, and then our real component is this negative root 3. Keep track of your negatives. It's really easy to lose those, and that can cause you some issues down the way. So this one's a little more complicated. We need to figure out what sine and cosine turn into 1 over the square root of 3. Okay, well, if we think about it, our sine should probably be, we know all of our unit circles, I hope, so our sine should probably be 1 over 2, which means that our cosine could be root 3 over 2, right? Because then if we flip this over, we get 1 over root 3, right? This comes here, and then we have times 2 over 2, so that's 1. So we get our 1 over root 3. But now we also need a negative. In this case, the negative is attached to the root 3, so we're going to follow that. We're going to follow that intuition and use that aspect. So we know we want our cosine to be a negative. So that means we want something either in quadrant 2 or quadrant 3. Now because we have a positive in the top, so this whole thing is negative, quadrant 3, everything's negative, so that's not going to work. So we know we need to be in quadrant 2. So now we need the angle that correlates to this sine and this cosine in quadrant 2, right? Well, if we remember, our cosine of root 3 over 2 occurs at pi over 6, and the same height is going to be when you take pi over 6 away from pi. So pi minus pi over 6. So we're going to get here 5 pi over 6. So now we have our r and our theta, we can write our polar forms. So our electrical engineering polar form, our phasor form, is going to be 2, 5 pi over 6, nice and easy. Or we can write it in the calculus version where we have 2, and then we have our parenthesis, cosine 5 pi over 6, plus I sine 5 pi over 6. Right? So we have 3 divided by negative 1 plus I. Okay? So this one's a little tricky. You can't just deal with it here, because we know this addition in the denominator means we can't break this up. We have to do something to be able to break this up. So we can't just take a real part of here and say, oh, I'm just going to ignore the I. That doesn't work. We need the I to be on top. And the reason we need that is because we remember that our complex number is equal to the square root of negative 1. And so we know we don't like square roots in our denominator. That's not nice. We don't like them. So we're always going to rationalize them. So the best way to rationalize this is in such a way where you get the i's to all cancel out and you get something I squared. And the reason why I want something I squared is because this is a square root. So when you get it squared, the square root goes away, you just get the number. So the way we're going to do that is by multiplying by the complex conjugate, which again is just where you take this sign between your terms and you flip it. So you have -1 minus I and -1 minus I, right? This is multiplying by 1. You can always multiply 1, you can always add 0. And then from here, it's just straight algebra. We're going to FOIL this out basically. Okay, so we're going to take our 3, multiply it in, so we get -3 minus 3i. Then we're going to divide by, now we have to FOIL this out, so we get -1 and -1 is +1. So we get -I and +I, so those are canceled. Then we get -I squared, which we'll write down, and then we'll simplify, okay? So now we have -3 minus 3i, and then on bottom, I squared becomes -1. -1 is +1, so we get +1. So now we have -3 minus 3i over 2. Now that works out nicely for us because with addition in the numerator, we can split that up. So now we can actually say that's the same as -3 over 2 minus 3i over 2. And that's useful because now we can take our real part and our imaginary part. Okay, so now that we're armed with the information we need, we can go ahead and decide our r, our radius of our polar number, is going to equal the square root of -3 over 2 squared, and then plus parenthesis -3 over 2 squared. Just be really careful with your parentheses and your negatives. It's really easy to make mistakes here. And also remember, you don't need the I, because when we're taking the imaginary part, it's everything attached to the I, but not the I itself. Okay, so this one's going to work out pretty straightforward. We're going to have 9 over 4 plus 9 over 4 is going to be 18 over 4. So the square root of 18 over 4 is going to be the same as the square root of 9 over 2, which is equal to 3 and the square root of 1 over 2, which is just going to be 3 over root 2. And then we're going to rationalize this. We're going to get 3 root 2 over 2. Right? Is that right? I think so. Yep, it is. Okay, great. So now we need to find our theta. So we have our inverse tangent of our imaginary part divided by our real part. So -3/2 over -3/2. Negative same thing over negative same thing is +1. So we get the inverse tangent of 1, which we already know from earlier. It's just pi quarter. Now, here's the tricky part. We know that this is sine over cosine, right? So if we have in our top right corner, sine and cosine are both positive. In our quadrant 2, cosine's negative, sine's positive. In quadrant 3, they're both negative. And in quadrant 4, cosine's positive and sine is negative. So these are negative going in, so we still need to respect that with our angle, even though we're getting pi-fourths out of it. Because even though these divide to be a +1, we still need to remember that they came from a sine and a cosine that were both negative. So even though pi-fourths is what we got out, we need to add pi to it to get to this quadrant 3. So we're going to go ahead and say pi-fourths plus pi. So this is one of those things when we do, especially engineering-facing math, we have to make sure we're paying attention to the physical reality as well as the math. So in this case, even though pi-fourths gets us the same tangent we wanted, it doesn't respect the physical reality. So we have to make sure we adjust for that. So now here we just get 5 pi over 4. Okay? Let's multiply together the first two numbers we got. Okay? So say, let's call this Z1. Interesting. Let's call this Z2, and we'll call this Z3. So first let's do Z1 multiplied by Z2. So if you want, you can go back to the original numbers we had and try and figure out how to do this just with those numbers in rectangular. You'll find it's kind of a pain in the butt. You'll have to FOIL and then deal with your negatives and make sure you're being really careful. Now what you can notice here is if we say, okay, well, Z1 is this root 2 angle pi over 4, and then I know Z2 is this 2 and then angle 5 pi 6. Well, here's the beauty of polar for us. We get to just multiply our magnitudes and add our angles. So we're going to get 2 root 2, that's just these magnitudes multiplied. And then we'll have our angle is pi over 4 plus 5 pi over 6, which we can solve out real quick. So least common denominator of these two angles is going to be 12 over 12, so we can multiply this guy by 2. So we're going to get 10 pi over 12, and then 3 pi over 12, so we get 13 pi over 12. Z2 times Z3, let's do that. Just another quick example, right? Okay, so Z2 is going to be this 2 with the angle of 5 pi over 6. I'm going to multiply that by 3 root 2 over 2 with the angle of 5 pi over 4. Okie doke. So again, we're just going to multiply our magnitudes and add our angles. So in this case, 2 times 3 root 2 over 2, 2's cancel, so we're just going to get 3 root 2. And then for our angle, again, we have 6 and 4, so we already know we're going for 12, so we're going to double this side, so we get 10 pi. And then we're going to triple this side, so we get 15, so we get 25 pi over 12. Now notice 25 pi is a little over 2 pi. So we're going to take out the 2 pi part. So this is actually going to equal 3 root 2 pi 12ths. We're going to do Z3 divided by Z1. Okay, so we have 3 root 2 over 2 with the angle of 5 pi over 4 divided by root 2 with the angle pi over 4. Now I'm hoping maybe we can kind of already see where this is going, knowing what we know, especially knowing now how to do multiplication of a complex number. But we're going to divide our magnitudes and subtract our angles. So 3 root 2 over root 2 over 1, the root 2 is going to go to the bottom and cancel out with this root 2. So now I get 3 halves. And then my angles are going to subtract. So 5 pi fourths minus pi fourth is just going to be 4 pi fourths, which is pi. Now, what's the most interesting with pi, let's write this in that other form. So we have 3 over 2 times cosine of pi plus I sine of pi. Well, sine of pi is 0, right? So there's no imaginary term in this one. Well, that's really interesting. So now we just have this 3 over 2 times cosine of pi. Well, cosine of pi is negative 1. Okay, well, so now that's just negative 3 over 2. And that's going to be our final answer for this one.